Welcome to this lesson in section 3.3. We're going to take a look at the antiderivatives of functions, part 2. In this lesson, our objectives are to consider finding antiderivatives using the integration rules. We want to find antiderivatives of indefinite integrals as well, and solve application questions using definite integrals. So let's go ahead and consider some indefinite integrals to start out with. So the first one we have on our list here is in part A. We have the integral of 6x to the fourth minus 9x squared plus 5 dx. So when we consider a power function here, we want to consider adding 1 to every exponent. And so in this case, we'd have 6x to the fifth raised to the, divide by 5. So we want to raise the power by 1, divide by that new power. We can subtract by 9, and then multiply by x to the third power, again divided by 3. And then finally, if we have a constant, we can imagine this constant is like x to the 0, 5 times x to the 0, and we would have an antiderivative of x times 5, or 5 times x. The next part, again, we'd want to consider is just adding that plus c constant to the end of that. This would characterize any antiderivative of this type, or this function. And so we could do a little bit of simplification here. 6x to the fifth divided by 5 minus 3x to the third plus 5x, and then plus c. So that would work for our antiderivative. Let's take a look at a second example here. We have the integral of the cube root of x to the seventh plus 10 times the square root of x to the fifth dx. One way we can consider starting with this is to rewrite this with radical or rational exponents. We could say this is the integral of x to the 7/3 to start, plus 10, and then x raised to the 5/2 power dx. So each of these, we can still use a power rule to consider their antiderivative. We can rewrite, we have x raised to, if we add 1 to the power here, we'll have 10/3. And then we'll want to divide by those 10/3 as a constant. Add to that, we have 10 as a constant multiple to begin with. X is going to have a new power here of 7/2 when we add 1. And then we'll divide by 7/2, the new power. Again, we can add the plus c constant to get any antiderivative for that function. If we multiply by the reciprocal of each of these fractions, we can get a new solution here. We'll do that for each of these to clean this up. And it looks like our final result we could rewrite here is going to be 3/10 and then x raised to the 10/3. We'll have plus 20 over 7 and then x raised to the 7/2 plus that constant c. So that would work for our solution for part B. Problem C takes a look at an integral with some product inside the integral. And we don't, again, know quite what to do with a product quite yet. So it might be helpful here to do some algebra before we consider this antiderivative. We can take the integral here of 3 times that x squared and the x squared times the negative 7x. So we'd have negative 7x cubed. So doing that distribution there just leaves us with, again, some power rule terms that we can work out. So it's always a good idea to try to simplify that integral before evaluating an antiderivative. So we have x to the third power divided by 3. And we have that 3 as a constant multiple to begin with. So that'll definitely cancel out later on. We have 7x to the fourth when we add 1 to the power and then divide by that new power again. So 7/4 x to the fourth. And then we can add our constant plus c. And when we're done, we can simplify this down to just x to the third minus 7/4 times x to the fourth plus constant c. So that gives us a nice form for our antiderivative. Next, we'll take a look at some definite integrals. Notice that we have some bounds attached to each of these integrals. So let's walk through each of these, evaluating them at the specific bounds. First, I want to find an antiderivative for the function. So let's start with that. We have 2x to the fifth first. We can raise the power by 1 to get 6, and then divide by that same constant of 6. And then we'll subtract 8x to the fourth power, and then we'll divide by the new power 4. Before we go to evaluate, it might be helpful here to just simplify what we've got. So this antiderivative, we can cancel out some constants. So we'll have x to the 6 over 3, and then 2 times x to the fourth. So let's just maybe write that down underneath. We have x to the 6 over 3 minus 2x to the fourth. And here we want to evaluate this antiderivative. This is our capital F of x function. We can evaluate this at the two bounds 4 and -2. So let's go ahead and evaluate this. The first value will be our capital F of 4. We have 4 to the 6th power divided by 3 minus 2 times 4 to the quantity 4. 4 raised to the fourth. We'll take this and subtract capital F of -2. So those two subtracted from one another. So we'll have -2 raised to the 6th power divided by constant 3 minus 2 times -2 raised to the fourth again. We'll end that bracket out. Now this calculation can be done in your calculator here. You can take a moment to do that if you'd like, to pause the video and try this out. If you go to your calculator, just make sure that this value, this should be right at 864. Should be the result for this calculation. So 864 would be the result for that definite integral. Again, this is showing us the area underneath this f curve, f of x curve, between the bounds of -2 and 4. So we're finding area underneath this curve. Let's set up another definite integral. This one is the integral from 1 to 2 of 1 over x cubed dx. This gives us another opportunity to rewrite this function inside before we go for our antiderivative. This is really x raised to the negative third power dx. That's helpful when we want to consider this antiderivative rule. We can take the antiderivative by raising the power by 1. Adding 1 to the power would be x to the negative second power. Then divide by my new power of negative 2. And before we evaluate this, it might be helpful to, again, rewrite this one more time. This would be the same thing as negative 1 divided by 2x squared. Because we'll bring that x to the negative second power down as a positive power in x. So here's where we can go ahead and evaluate this at 2 and at 1. So first we'll evaluate, again, f at 2. Here's our capital F function again. We've got negative 1 divided by 2 times 2 squared for our first one. Then we'll subtract negative 1 over 2 times 1 quantity squared. So both these quantities will be negative. So we want to be careful to watch for those. So it looks like we have the result of negative 1 over 8. We'll have a double negative in the second term to make it positive. And that will be 1/2 plus 1/2. So 1/8 added to 1/2, we can get a little common denominator here to get this going. If we multiply by 4 over 4, do a little bit of algebra just to get this on paper. We've got negative 1/4 plus 4/8, and that ends up being here for us 3/8. So we'll just grab 3/8. So there we go. So we have 3/8 units of area underneath the 1 over x cubed graph between the interval from between 1 to 2. Let's go ahead and do one more definite integral before we look at some applications. This one, again, actually we'll have two, part C and part D. Part C takes a look at an integral from 2 to 5 of a product of functions, t squared plus 4 and 2 plus t dt. So again, since we have a product here, it might be helpful to do some algebra prior to taking this antiderivative because we don't know quite what to do with this product. So we'll have to work through some algebra first. So I'm going to take this to the side, grab my t squared plus 4 times 2 plus t, and we'll just do some multiplication. So I'll do just a little bit of foiling here to get this started. We've got 2 times t squared plus t to the third, and then we'll have two more products with 4 times 2 and then 4 times t. So it looks like all of these terms will have, there's no like terms in this grouping of 4. So we'll just keep these individual or separate. We've got the integral from 2 to 5, and I'll just write this in order just for ease of use. So that was t to the third plus 2t squared and then we'll have 4t, and then plus 8. That's just a habit to get into. It's kind of helpful just to organize your terms if we just write them from least to greatest in terms of power. So let's go ahead and try for these antiderivatives. First, we'll have antiderivative for t to the third will be t to the fourth over 4. We have plus 2 times t to the new power of 3 divided by 3, and then plus 4 t squared divided by 2. And then finally, for the constant 8, we'll just tack on a t. Here again, we don't have to have our constant plus c because we're going to evaluate this antiderivative right here. I'll just do this one little adjustment to our function here. This 4 and 2, we can cancel to just a 2t squared. So when we rewrite that, we can just have a 2t squared when we're done. So we're going to want to evaluate again this function from 5 to 2. And just for space considerations, I'm going to jot this down below. We want to find f, capital F at 5, and then we'll subtract capital F at 2. So let's do, just write this out on paper. So we've got 5 raised to the 4th over 4 plus 2, 5 raised to the 3rd over 3. And then we have finally 2 times 5 squared, and then plus 8 times 5. So that'll be my f of 5 right there. And just to maybe distinguish where we stop and start here, let's even add some colors. We'll add the red here. This is going to be my f at 2. So we'll do the same evaluation, but now evaluate at 2. So we have 2 to the 4th over 4 plus 2 times 2 to the 3rd divided by 3, and then plus 2 times 2 squared, lots of 2's in this one, and then plus 8 times 2. And we'll end that bracket. All right, and if we go again, we can try to evaluate this in your calculator. If you want, you can pause here and try this evaluation in your calculator if you want. If you do so, we should get an even value here, 296.25 as our final result. And that should give us that complete area underneath the cubic curve here from 2 to 5. We do have one more definite integral to consider here in part D. So part D, we're considering a quotient here. The integral from 0 to 4, we have the function 4x squared plus x divided by that square root of x dx. So like before, we had some operations like a product in part C. Here we have a quotient in part D that we might need a handle before we consider taking the antiderivative. So let's consider first how I would rewrite this quotient to just simplify this down to something I can work with. So we know that x raised to the 1/2 power is equivalent to the square root function, and we'll want to use this when rewriting. So we have the integral from 0 to 4. If I divide by x to the 1/2, I'm going to consider just subtracting 1/2 from each of the powers. I have 4 x squared, and then if I subtract a half power here, I would end up with just x raised to the 3/2 in that first term. So that first term sitting right here. If I move over to the second term in the numerator, we have our x to the first power divided by x to the 1/2 is still going to be x to the half here. So we still have x to the half power dx. So now we have just a sum of two individual terms in that function instead of a quotient. So let's go ahead and take the antiderivative of each of the terms. We have 4 and then x. We started with a power of 3/2. If I add 1 to that, we should get 5/2. And then we'll divide by that new exponent of 5/2. Add to that, we have now x raised to the 1/2 becomes x raised to the 3/2 when we add 1. And we'll divide by 3/2. Now, this one is also going to be helpful to maybe rewrite initially before we go to evaluate from 0 to 4. So I'm going to, again, multiply by 2/5 for this first one. We'll cancel out some fractions, and then we'll multiply by 2/3 to receive our result for that second term. So looks like our final results for that antiderivative are going to be 8/5 times. Here, x raised to the 5/2. We can actually rewrite this in a little bit simpler form when we go to evaluate here. Since we're going from 0 to 4, we'll have kind of some perfect squares here. So we can look at this as x to the 5th underneath the square root. So that 2, the 1/2 in that exponent, can be a square root. And so 5/2 would be the square root of x to the 5th. We can add to this, we have 2/3, and then 3/2, we can consider this as the square root of x to the 3rd power, would be the equivalent. And at this point, it looks like a good time to, again, evaluate this function at our endpoints. That would be 0 and 4. So let's go ahead and evaluate first at 4, and then we'll evaluate at 0, which should actually just get us a 0. So first value, again, capital F of 4 for us. We have 8/5, and then the square root of 4 raised to the 5th. And then we'll have plus 2/3 times 4 raised to the 3rd power. And we'll subtract from that the capital F at 0. That's our second endpoint. But notice that if I evaluate 0 in both of these functions, that's actually just going to get me a 0 back. So I'm really going to just be subtracting 0 away in that second endpoint. So what we have here is actually going to be our result. So let's go ahead and maybe just jot down some values to get us going, to simplify this up. Okay. One way we can rewrite this is we have 8/5, and then the square root 4 raised to the 5th power. If you find that, that should be 1024. Plus, we have 2/3, and then 4 times itself 3 times ends up being just 64. So square root of 64 there. Now, 1024 is not a perfect square root, so we can't simplify that any further, at least in the root. We certainly can break down maybe a little bit more, but it's not a perfect square. 64 is the perfect square. That's going to be 8 for us, so you certainly could rewrite this if you want with that same root and plus 2 times here, this is going to be 8, would be 16 over 3. So this would be kind of an exact result, and we'd have to get a common denominator if we wanted it into a fraction form. If we want just a approximate solution to this, let's maybe just find that in our calculator here. We would get this as 56.33 repeating. Another way we could rewrite this as a fraction if we want. If this is 56 and 1/3, we wanted an exact fraction here. We could take 56 times 3 and add 1. So if we quickly do that, I'll just do that on the side. I don't have that in the notes, so we'll just try that. Looks like 168, and then we want to add an extra third there. So I think an equivalent fraction there would be 169 over 3. We could get that as well. So that would be a more exact fraction result. All right. Oh, excuse me. I think that was wrong. That should be 58, 56. So it'll be a little bit different on the fraction. So let me backtrack there. Don't want to lead you guys astray there. It should be 5-3 repeating. So we'll just keep that as 5-3 repeating there for the approximate solution there. So we can disregard that other fraction work. All right, so we have a couple applications we want to finish this lesson up with. So this considers a marginal profit function. So this says a company's marginal profit is defined as P prime of x is equal to negative x squared plus 45x plus 10. We want to find the company's profit for selling their first 50 items. So let's just consider again that x again is maybe the quantity of items here. And we want to know, well, what's actually the total profits if we know this marginal profit function. So one way I can consider doing this is we can set up an integral from 0 to 50 and integrate the marginal function. So we can take our marginal function P prime of x dx and integrate that from 0 to 50. So here we know our marginal function, so I'm going to just fill that in to the function in the integral, and then we'll go ahead and apply that antiderivative. So we have negative x squared plus 45x plus 10 dx. So we'll take that antiderivative first. We can say that this is going to be negative x to the third over 3 plus 45x squared over 2, and then plus 10 times just an x power. We'll evaluate this definite integral at 50 at our upper endpoint and 0 at our lower endpoint. So first we'll go for, really this is going to be p of 50, and then minus p of 0. So when we go for our P of 50, again, this is really going to be our total profits for those 50 items. Notice that P of 0 will actually just give us 0 itself. So we just want to evaluate this first grouping. We have negative 50 cubed divided by 3, plus we'll have 45 times 50 squared divided by 2, and then plus 10 times 50. And again, this P of 0, if we evaluate 0 for this function, that actually goes to 0 itself. So there's nothing going to be subtracted from this P of 50. If you go ahead and put this into your calculator, you can try this if you wanted to pause here and try to evaluate this on your own first. If you go for this result rounded to the nearest cent here, we should get $15,083.33 for that total profit for the first 50 items. So that would be, again, another way of saying capital P of 50. The second part to this question considers, well, how much will the first 50 items profit the company on average? So if I wanted to consider average profit for those first 50 items, we know average profit is P bar of 50, which is the total profits divided by the number of items that I've sold, which is 50. If we do this calculation, again, P of 50 is found in the previous problem, and divide by 50 items, we end up getting approximately $301.67 per item for that average profit. So we'll average just over $300 in profit for each of the first 50 items. So that would complete this problem that starts with our marginal profit function. The last question we're going to consider is what we would call a initial value problem. Initial value problem. So this tells us the following, that the rate at which the number of new driver's license issued by the Payson DMV is changing according to the function d prime of x, which is equal to negative 30x plus 125, where this is measured in licenses per year. So the number of licenses per year is changing here. Where x is the number of years after 1990, we want to find an equation that gives the total number of licenses issued by the issued in Payson if there were 5,000 licensed residents in 1995. In other words, the D of 5, the number of driver's license, 5 years after the starting point was 5,000. So let's go ahead and consider how we would actually solve for this d of x function. We want to know the actual equation for d of x, the number of driver's license for a given year. Again, here, notice that x here is the number of years after 1990, or after that starting point. And the output for d of x would be just the number of licenses. So we can actually find this d of x by integrating our d prime function. So we have the marginal function d prime, And we will go ahead and integrate this d prime function. So in general, what we'll have is the integral of d prime of x dx, but again, we know this quantity, so we can say that this is just going to be an integral of negative 30 x plus 125 dx. And here I'm going to kind of leave this as an indefinite integral first, and I'll show us why this is just going to be an indefinite integral in just a minute. So antiderivative here is just going to be taken as negative 30 x squared over 2, and then plus 125 times x. And then again, this indefinite integral would have some constant plus c at the end of this for the d of x function. So we actually just need to solve for, well, what is that constant c for this capital D of x function? And the way that we're going to figure out what that specific constant is by using that initial condition. So we haven't actually used that initial condition yet. So we'll have to try to use that now. We know in 1995, or x is equal to 5 years, that there were 5,000 licensed drivers in Payson. So we'll use that kind of xy value here to get to that constant c. So we can say that there were 5,000 licensed drivers, that's our output, when, looks like we have negative 15 here, we had an input here of 5 years. So input of 5 years, x is equal to 5, when our output was equal to 5,000. So we'll kind of finish that up with these. So we have 125, and then again times the input of 5. And then we'll need to solve for that plus c. So we only have one variable, that constant, to solve for. So let's look at that. We have 5,000 on the left equals, we'll have negative, and this is squared. Sorry, I didn't grab that. 5 squared here. So negative 15 times 25 here. And then 125 times 5. I think when we add both of these up here, we should get 250 plus c. 250 plus c. And if we subtract that 250 value to both sides, we'll get our constant value, and that looks like 4,750 for that constant c. So when we go to describe our final d of x equation here, the licensed drivers will be now defined with the expression negative 15x squared. So we're taking this original function plus, we'll have that 125x, and then the constant c that we just solved for was 4,750. And this would be outputting licensed drivers. There we go. And then again, x measures the years since 1990. There we go. So that would be our function. That would be an initial value equation, and we want to consider that with an indefinite integral. So, thanks for watching this video. Please reach out if you guys have any questions, and I'll see you guys in the next video for 3.4.